Hi everyone, and welcome to my look at size perception, which will tie into depth perception as well. Let's take a look at some bottom-up influences on size perception, going to a classic experiment that was done in a hallway, and it was interesting. Okay, so the major name here is Edwin Boring. This is a picture of him. In this task, which was, yes, done in a hallway, people had to adjust the size of a comparison circle to match that of a bunch of different sized test circles. Now, these circles are placed at different distances away from the observer. There's a picture. Yes, it was done down a hallway. Here's the comparison circle, okay? And then people were given a number of different test circles. But the test circles were carefully arranged in terms of their size and distance so that the visual angle of all the test circles was the same, 1 degree of visual angle. Now that means each 3 of these test circles is casting the same size image on the retina. The big one far away, the medium one at a medium distance, and the little one that's the closest. Okay, same retinal size or visual angle. Part 1 is the normal viewing condition, and people were just really good at this. So if the test circle was large and far away, people chose the large disk. Again, the task is to match the size of the circle. In part 2, they eliminated depth cues, and that explains this line here. This line was a curtain. Now, the curtain was put up down this part of the hallway, and there was a little peephole, and that peephole was 1 degree of visual angle. That is, it was just big enough to accommodate the different test circles at their different distances. Okay, so what this does is it removes any depth cues. You can't use accommodation, you can't use convergence, you can't use binocular disparity, you can't use anything. There's nothing there. All you can see is this black circle. Now, because all of these test circles had the same visual angle, people said that they all matched the comparison circle, rather. They said that the small disk that was close was exactly the same size as the comparison, and the medium-sized disk at a medium distance was the same size as the comparison, and the large disk that was far away was the same size as the comparison circle. In other words, people cannot tell what the actual size of the test circles was. Why? Because they were deprived of all depth and distance information. Okay, this is pretty clear evidence that our perception of size is dependent on knowing depth information. That's a form of bottom-up processing. But now that we've seen bottom-up processing, let's see the influence of top-down processing. My favorite example comes from Jerome Bruner and a colleague in 1947. They recruited 10-year-old children to estimate the size of coins. And they did this using an adjustable disk of light. Okay. So we have disks and we have coins. The disks referred to cardboard disks. Okay, and these disks were made to be exactly the same size as a penny, a nickel, a dime, and a quarter. And they weren't perfectly accurate, but they were pretty close. 0 would mean that you are bang on. You're not making it too small or too big. They're pretty close. These are the cardboard discs. Here are the coins. You can see that children are vastly overestimating the size of the coins, and it goes up depending on the denomination of the coins. So they're overestimating the size of a penny by about 16%, but a quarter is overestimated in terms of its physical size by about 37%. Interesting. How are cardboard discs and coins different? Cardboard discs ain't worth nothing. But coins. In 1947, for 25 cents, you could probably get a house or something. So this is clear evidence of top-down processing. It's the monetary value of the coins that is contributing to the overestimation of the size. And then they did an interesting thing. They broke down the kids. Now, back in 1947, they called them rich and poor. We wouldn't use those terms these days. We'd use something like socioeconomic status. Here's the difference between the rich kids, the solid line, and the poor kids. So poor kids don't have a lot of money. It looks like they very strongly value money more than the rich kids. Okay, so in 1947, a penny could still buy you stuff. But still, look at the difference in the rich kids and the poor kids. Now they're all overestimating the size of the coins, but the poor kids even more. Again, this really strongly shows the influence of top-down processing, even for something as simple and basic as judging the size of a stimulus. Now, in general, we are pretty good at perceiving the size of objects, and that brings me to our next perceptual constancy, size constancy. Now, size and distance are intimately interrelated. If I'm talking to my friend George, and then he walks away, the size of my friend on my retina gets smaller with each step that he takes. But I don't say, "Hey, George, man, you're shrinking." Even though the size of his image on my retina is getting smaller, because I also can see that his distance from me is increasing. So somehow my visual system takes both of these pieces of information into account. This is called size-distance scaling. Now we have to have information about distance, or our perception of size is completely out of whack, as Holloway and Boring showed. Now, sometimes we can get some neat things that happen, like illusions. A lot of illusions are actually the result of a misapplication of size constancy. A lot of these illusions exist on paper, that is, they're two-dimensional. Not a lot of them exist in the real world, but we'll come back to the real world. But first, time for illusions. Okay, this is called Terror Subterra, created by Roger Shepard, and it's a big monster who is chasing a clearly smaller monster. But if you consider the size of the monsters on the screen, as opposed to in 3 dimensions, let's take away all that background. Yeah, those two monsters, they are exactly the same size on the screen. Now, some artists do like to play with this a little bit. Here is Julian Beaver with his work Swimming Pool in the High Street. And it looks like he's about to jump into a pool. Okay, it's actually a chalk drawing. And it's a chalk drawing from a particular angle. Let's take a look at it from the reverse angle. Whoa, lady, you got a big leg. Okay, so from one angle and one angle only, it looks like it's a normally proportioned woman. But from the reverse angle, you can see that he's had to largely distort her foot to get her to look normal from that one angle. Here's another example from his website. It's called Make Poverty History. He was invited to a world conference, and he made this chalk drawing. And let's take a look at that from a different angle. Yeah, that Earth is not a sphere, not even close. Now, some people have tried to do this in other environments. So this looks like you're walking down a hallway and you're going to run into kind of a transparent sheet. But actually, no. All that red color you see is painted onto the ceiling and onto the walls. You can just walk straight through that. Pretty cool. This is a famous illusion, the Miller-Lyer illusion. Maybe you're familiar with it, huh? Yeah, am I right? Okay, it dates back to 1889, and of course the illusion is that trying to ignore the arrowheads or the wings, or whatever you want to call them, the straight line segments of A and B are exactly the same length. But it looks like the one on A is a bit longer, and the one on B is comparatively shorter. This is a pretty robust illusion. But why? Why do we get this misperception of size? Richard Gregory, who was a constructivist, looked for some form of top-down processing that may affect our perception of the size of these lines. Now, through extensive testing, it was determined that the illusion is weaker in children than in adults generally. And if you compare people in the UK to people who live in other environments, like dome-shaped huts, the illusion is much weaker in people who live in these kinds of environments. Dome-shaped huts versus Western dwellings. Well, let's take a look at a typical Western scene. Hidden in here is the Miller-Lyer illusion. Can you find? Okay, it's not really hidden. It's right there in front of you. Okay, so what we have is the Miller-Lyer illusion with kind of outward pointing arrowheads and then the inward pointing. Now, if we just focus on the vertical line segment, for this one here, it's pretty tall. It goes from the floor all the way up to the ceiling. What is that, like, I don't know, 2.5 meters? This one here, clearly it's a lot shorter. It's maybe about 1 meter or so. Now, this one on the left seems longer because we perceive it as being farther away. The one on the right seems shorter because we believe it to be closer. Let's remove a bunch of the stuff here. Okay, there's the basic Miller-Lyer illusion. I haven't changed it at all. Let's go back and show you. Okay, yep. Now let's check and compare the vertical lines. Yep, they are actually exactly the same size on the screen. But we have this very different perception of them in terms of 3 dimensions. So again, distance and size work together. Gregory's explanation for the Miller-Lyer illusion is called the carpentered world hypothesis. The Western world is carpentered. That is, it is built out of straight pieces of wood, and there are a lot of 90-degree angles. So, A is like the inside corner of a room. It's concave. B is like an outside edge. It's convex, I guess. So, again, these implied depth cues suggest to us that A is farther away, B is relatively close. Our size constancy scaling mechanism kicks in. We can't help it. It kicks in automatically. And because A seems to be farther away, we perceive it to be longer. Just think about that again. A is believed to be farther away, but we perceive it to be longer. B we believe to be closer, so we perceive it to be shorter. Yes, I did get that right. I didn't make a mistake. Now, this is a brilliant explanation of the Miller-Lyer illusion, showing the influence of top-down processing. But what about this? Some people call it the dumbbell illusion. It's the same kind of a thing. People perceive the bottom horizontal line to be longer than the top horizontal line. But there are no room angles or corners or edges. We can't really apply the carpentered world hypothesis to this. So what's going on in the dumbbell illusion? Nobody's come up with a satisfactory explanation yet, unfortunately. Now, a lot of people sort of criticize these illusions because they're two-dimensional. They're on paper or they're on a screen. It's not like it's in the real world or anything, so we should give our visual system more credit for working so well in the real world. Are there illusions in the real world? There actually are, and one of the strongest is called the moon illusion. I'm going to tell you about it, and if you actually look outside on a dark night and see the moon, you're probably not going to believe me, but I swear it's true. The illusion is this. The moon, when it's at the horizon, seems to be larger than the same moon when it's at its zenith. That means when it's directly overhead. The thing about the moon is the retinal size of the moon, which is just a scooch over half a degree of visual angle, and its actual distance are basically constant. It varies somewhat, okay, I do admit that, but it doesn't vary so much that you can notice it, say, over the course of an evening, looking at the moon, starting at the horizon, and then this is a series of photographs until it reaches you overhead. You can't perceive any kind of difference in the moon. So why does the moon illusion exist? Now, there are explanations dating back literally centuries. The argument is that it's once again a misperception of distance. So this is something that I've shown you before, but I'm going to show it to you again. Okay, in the left image, we have an eye looking at a large object far away, and in this case, a small object that's close to us. So, if an object is perceived to be farther away, or if it even is actually farther away, and if it has the same visual angle as an object that is perceived to be or is actually closer, then the farther object will appear to be larger. Okay? This has been true of the illusions that I've shown you. This is true of the Miller-Lyer illusion. Again, the visual angle of the straight line segments are identical. That's something that you have to keep in mind. So there are many explanations that try to account for the moon illusion. Let's go to this one. It's called apparent distance theory. And it considers what's the difference between the moon at the horizon versus the moon when it's overhead. Really, what is the difference between those two? So if you think about looking at the full moon, it's on the horizon. Well, you have to look across the ground. There's all this stuff, right? So there's trees and maybe buildings and clouds, and then behind that, there's the moon. But if you look at the moon when it's above you, at the zenith, what can you compare the moon to? You really can't compare it to anything. Again, when it's at the horizon, you can see that the moon is behind this building, and that's a big building, and it's behind it, and it's behind clouds. Wow! When it's at the zenith, what can you compare the moon to except clouds? Maybe, kind of, sort of. So, according to apparent distance theory, the moon at the zenith should appear to be closer. Once again, I bring in Edwin Boring. Now, don't make fun of his name. I'm not going to make fun of his name. My name means spoon man, okay? So I'm not in a position to make fun of anybody's name. In fact, Edwin Boring was kind of a big deal in perception in the middle of the 20th century. And you didn't want to cross him. Not that he was mean or vindictive, but if he found an experimental result, you really didn't want to go against that, because otherwise your career would be kind of at a dead end. So, in 1940, Boring set up an apparatus so that observers could view projections of the moon, not the real moon, but a projection, so you have complete control over that. You don't have to wait until it's a full moon. You don't have to worry if it's cloudy, anything like that, okay? Precise experimental control. And when people viewed these projections of the moon, they reported that the horizon moon looked closer than the moon at its zenith. Now, this is a contradiction to the prediction made by apparent distance theory. Haha! Boring, as always, must be right. Apparent distance theory is wrong, okay? He's just blown it away with this experimental evidence. Now, he went up to the observers and he asked them, why do you think this is? And they explained that the horizon moon appeared to be larger. Okay, so Boring, in thinking about it, wanted to propose his own theory. He came up with the eye elevation hypothesis. So this is the idea. What is the difference between the moon at the horizon and the moon at its zenith? When the moon is at the horizon, you're just kind of standing normally and you're just looking straight. Your eyes are just like in their normal position in your eye sockets. But when the moon is above you, you rotate your eyes up in your eye sockets, and that somehow makes things look smaller. How does that work? Shut up. It's a hypothesis. Shut up. Just accept it, okay? Boring said so. Okay, so this is his hypothesis. He then, to his credit, experimentally tried to find some support for that. Okay, so he had observers, once again, compare the size of projections of the moon. When people looked up at the zenith moon, the moon appeared very small. Then he had people, and this is crazy, he had them lie down on a table. So when you lie down and your eyes are just looking straight, well, you're looking straight up into the sky. And he very carefully adjusted the table they were lying on so that they were at the same standing eye height as in the first condition. And now in the second condition, the moon seemed to be larger. Whoa. As bizarro as eye elevation hypothesis seems to be, Boring has just found experimental evidence to confirm it. This is not the same thing as explaining it. So why is it that when you rotate your eyes up in their sockets, it makes things look smaller? Are the bones of your eye socket compressing your eye or something? It doesn't really explain why, does it? But hey, it was boring. You had to accept it. That wasn't a pun or anything, okay? I'm not making puns. Now this idea lasted until 1962, when Kaufman and Irving Rock tried to replicate Boring's eye elevation hypothesis results, and they couldn't. They couldn't replicate it. The difficulty seemed to be that it was very difficult for people to match the size of faraway objects like the moon. So the problem, as they saw it, was, does misperception of size cause the error in the judgment of distance? Or does misperception of distance lead to the error in the perception of size? Yeah. Well, Kaufman and Rock proposed an alternative that is based on two components. The first component is Emmert's law, which dates back to 1881. Emmert's law, you know what? I already showed it to you. What? No, you didn't. Yes, I did. I just didn't call it Emmert's law. Again, this is something that applies when we're looking at an object that has a constant visual angle. Like the moon, it has a constant visual angle. But if we believe the moon to be farther away, we will perceive it to be bigger. If we believe it to be closer, we will perceive it as smaller. Okay, we just need to fill in one thing. What leads to our belief about the distance of the moon? Because it does all hinge on that. To fill in that, they had to go back to the work of Claudius Ptolemy in the year 130. Claudius Ptolemy was a Greco-Roman mathematician, astronomer, geographer, and astrologer. He lived in the city of Alexandria in the Roman province of Egypt. He wrote in Greek, and he held Roman citizenship. I didn't know this would be a lesson in that. Yeah, I know, but I just thought I'd let you know. Claudius Ptolemy. Ptolemy believed that planets don't just hang in space. That's crazy talk. How could something like so big just kind of hang there in space? No. Things are embedded in transparent heavenly spheres. So like the moon, it's not just hanging there in the sky. No, it's embedded in a transparent sphere. And when that sphere moves around the Earth, which is the center of the universe, obviously, it takes the moon with it. Now, to make all of these things work, Ptolemy proposed that the sky has a shape. And the term for this is the vault of the heavens. So the sky does not extend off to infinity in all directions. I thought that was the definition of the sky. Yeah, okay, it actually is. But Ptolemy believed that the shape of the sky is kind of like an upside-down cereal bowl. So the sky above you is kind of flattened, and it's actually closer to you than the sky that's at the horizon. So the moon travels along that path. The moon travels along a flat sky, so the horizon appears farther away. Oh, wait, sorry, I'm missing a Y. Let me put the Y back. The horizon appears farther away. Okay, that makes more sense. Yeah, okay, I know all this Ptolemy stuff is kind of crazy, but it would account for the data that we get, the data that Kaufman and Rock obtained. Let me show you a picture. Okay, so here we have our pretty good-looking observer, I gotta say, standing on the Earth. Okay, and here's the actual path of the moon. The moon is like, it doesn't change in its distance from us, okay? This is the actual path, but here's that vault of the heavens. When the moon is above us, the path is a bit flattened. So this is the path that we perceive the moon taking. Now at the horizon, it turns out we're actually accurate. We perceive it to be far away. It's actually far away. The problem arrives here when the moon is at its zenith. We believe the moon to be closer, so we perceive it to be smaller. Once again, size constancy has kicked in. Now, this is not a full explanation because it doesn't account for why do we believe the moon to be closer when it's directly above us. That's a bit trickier, but it seems to be due to clouds. Clouds, when they're directly overhead, are actually closer to you than when that same cloud, all other things being equal, is at the horizon. So when it's above you, it might be, I don't know, half a kilometer, but you can see clouds that are many kilometers away. So we have a lot of experience with clouds, and we somehow transfer that knowledge onto the moon, and we believe the moon moves like clouds. So once again, it is this kind of interplay between bottom-up processing and, yeah, that's right, top-down processing. All right, I want to sneak this last thing in here. It's the field that I work in now. It is human factors and ergonomics. So it is legit for me to be talking about this because this is a branch of psychology. It overlaps with design. It also overlaps with engineering. It's about designing things based on what we know about people's perception, cognition, and behavior. So specifically designing, taking all of these things into account. The goals for human factors and ergonomics are safe and comfortable and efficient and effective human use. And this picture is a bit of a preview for the specific domain that I want to apply human factors to. So here's some information on grade crossing accidents. So I have data from the US, and the most recent data I have is from 2018. There were over 2,000 collisions at rail crossings, resulting in 270 fatalities and 819 injuries. I also have data from Canada. There were 236 rail crossing incidents, 53 fatalities, and 72 serious injuries. Now, of course, we don't want anyone getting injured or killed at these intersections between vehicles and trains. But why does that happen? And why does this continue to happen? So for that, I turn to the legendary Herschel Leibowitz. It's not that people are dumb. That doesn't explain anything. Rather, there might be some perceptual and sensory factors at work. One is the illusion of velocity and size. In general, we believe that the bigger something is, the slower it moves. And this is, to some extent, generally true. So a fly, it's tiny, moves really fast. Elephant, it's very big, moves very slow. You know the thing about a freight train? They can move pretty fast. And passenger trains can also move really, really fast. So because it's so big, we have this misconception that it's actually moving pretty slowly. Secondly is the illusion of linear perspective. This increases what we perceive to be the distance of the train, how far away it is, and this then plays into the time that we think we have available to get across those railroad tracks. Again, there's linear perspective for you. And there's a third one that's a bit more tricky to kind of wrap your arms around. Leibowitz calls it the deceptive geometry of collisions. Now, as that train gets closer to you, the retinal image size increases, and this is called looming. Now we can take a look at the rate of increase in size. It's not a linear function, it's a hyperbolic function. And that's a bit tricky for people to handle. People are okay with linear functions, but hyperbolic functions, that's a bit difficult for us. So, in other words, when the train is really far away, it's barely increasing its size on your retina, and you have this belief of, it's slow, it's really not moving very fast at all. Once it gets closer, that looming increases exponentially. And by the time you realize, whoa, it's coming at me really, it's too late. Like you haven't given yourself enough time because of your misperception of the train. So we could just go, oh well, people are going to misperceive, and some people are going to be injured and some are going to die. No, there are things that we still can do. So this is where the human factors comes in. Now we realize that we can't change our basic visual processing, but at the very least, what we can try to do is make people aware of things. Operation Lifesaver is a public awareness campaign which is telling people about these kinds of illusions, if not necessarily explaining them in detail, but basically telling people be safe when it comes to these railroad crossings. This first began in 1972, and since then, train and vehicle collisions have decreased by an astounding 81%. Might not have been the only thing at work, but it's probably contributing at least somewhat. All right, thanks for watching. Go check out the E-Class lecture quiz.